Okay, hello everyone. Today I want to show you how to do performance profiling with Tracy for Mutter, GNOME Shell, and your apps. My name is Molodetskikh. By day, I'm working on a PhD in computer vision, but in my free time, I've been a long-time contributor to open source and free software. I usually tend to lower-level components, such as compositors. In GNOME, I worked on improving the input latency in Mutter a while ago. I also implemented the screenshot UI in GNOME Shell that landed a few releases back. And I also have two GNOME Circle apps, Video Trimmer and Identity. Also, for the past 3 years almost, I've been creating my own Wayland compositor called niri, which has a unusual windowing paradigm where your workspaces aren't limited in size to your monitors, so you can scroll them left and right, as you can see. Also, in 2023, I participated in the grant from the Sovereign Tech Foundation to GNOME. That was a €1 million grant to improve various parts of GNOME. And my part was to do performance profiling and optimization for Mutter and GNOME Shell. I managed to identify 12 performance problems and fixed 7 of them, which considerably improved the smoothness of GNOME Shell. So thanks to STF for that. For that work, I used Tracy, which is a profiler by Bartosz Taudul. It is a frame profiler, mainly for video games, but it has a lot of very useful visualizations and statistical functions, and I found it quite useful for doing this work. So don't be scared by this overcomplicated screenshot. It just has a lot of panels open all at once. I will try to explain to you how to use it step by step. So the main thing to understand about Tracy is its timeline view. This is the main view. Here, time is flowing from left to right. And on the timeline view, we see these rectangles called zones. So they indicate where some part of the code starts and ends. So the zone starts here and then ends here. And the zones are nested. So here we can see a recording from Mutter. It has a function clutter frame clock dispatch, which calls clutter frame listener frame. And this is visualized below that parent zone. So the zones are nested. You can see what a piece of the code is doing and where it's calling into. So we already have a profiler in GNOME called sysprof. So what's the difference? Well, it turns out that Tracy and sysprof largely collect the same data, and even these zones in Tracy are pretty much the same as marks in sysprof. The main difference is that the Tracy zones must nest correctly, so the child zone must end before its parent zone. In sysprof, there is no such requirement, and this affects the way the zones are visualized. So in Tracy, it can show this nested view. And in sysprof, it has to show like the marks chart or the marks waterfall. And in my opinion, the Tracy timeline view is very useful for diagnosing individual frames and other performance problems. So let's look at an example from the STF. There was one problem where Shell was becoming very laggy over time. So as you use the Shell, it became more and more stuttery. And I want to shout out and say a big thanks to Jeff 14, who you may know from our GitLab issues and project management. Jeff has a slightly older hardware setup, and so he was hitting a bunch of those performance problems. And he really helped me with diagnosing them. So he was recording Tracy profiles for me to analyze. Then I would propose some fix, and Jeff would test it and see if it worked. So I went to dig matrix DMs to look up the details of this problem, and well, unfortunately, it loaded on another computer. So this was what I found. This is from the trace that Jeff sent me, and in GNOME Shell, as you may know, much of the UI is written in JavaScript, in GGS. And so when you do some keyboard input or mouse input in the overview, it goes through JavaScript handlers. In this case, STWidget event calls into JavaScript onCaptured event. And what I found is that onCaptured event was calling into a lot of tiny functions. So in this case, 4,500 functions, which was taking 43 milliseconds, which is like several frames long. You definitely don't want your input handler taking this long. So I zoomed in, and indeed, all of these individual functions were tiny, they're barely registered, and they were coming from this pop-up menu manager. So I suspected it was some kind of signal leak where the pop-up menu manager was connected to something, and then the code forgot to disconnect it, so they all piled up. And after a few days, you had 4,500 tiny JavaScript callbacks. And indeed, the fix was to disconnect the handler in the correct place, and the fix worked. Jeff reported that it was one of the biggest performance improvements. And the way I was able to quickly identify this issue is by looking at this timeline view, which let me inspect individual frames and individual functions and see that within this one function we have a weirdly large amount of nested calls. So hopefully I've piqued your interest. So how do you actually use this? Now, much like sysprof, Tracy has two components. The profiler UI application itself, which is this application where you actually view the profile, and also a library, libtracy, linked into the target program, which collects the data and which provides you with functions to instrument your code. Now, Tracy is aimed primarily at game development, where it's common to build from source and bundle your dependencies. So it's not really packaged in distributions, but for Fedora, I made a copper where I have pre-built both the UI and libtracy. Also, Tracy has a very extensive manual. If you have any question, it's probably answered in the manual. If you're interested, I recommend you to check it out. So let's say that we have an example of project in C, GTK Hello World application. Now, Tracy's primary language is C++, but it also has bindings to C and some other languages. And so it provides integration to both CMake and Meson out of the box. So it's very easy to add to a C project. Just add a dependency in Meson. Also add a rep file pointing at its repository. Now, at the time of this talk, the latest stable version is 0.13.1, and since then we've landed a few fixes, for example, to symbol resolution. So here it's pointing to a newer Git version, but once the next version is released, you can switch it to the stable version. So then we will use the C API, so include Tracy, tracyc.h. And then let's say that we are building our UI in a GTK application. So we connect to the activate signal with this activate function, and we want to measure how long this function is taking. So we surround it with the Tracy C zone. These two macros, Tracy C zone starts the zone, Tracy C zone ends the zone. They take two arguments. The first one is just a variable name for the zone to store the zone in, and the one is whether the zone is active in case you want to do some dynamic toggling. Also, as I mentioned, Tracy zones can be nested. So let's say that we want to measure this GTK window present call separately from the rest of the function. So we want to see how much of this function is taken by GTK window present specifically. For this, I'm using the Tracy C zone n macro. The n allows you to pass a explicit zone name, in this case window present. If you use the normal macro, it will just use the name of the function. So if you were writing this in Rust instead, there's the Tracy client crate, which wraps libtracy and provides you with a nice API. Here's the same activate callback, and you would write Tracy client span. Here span is just a different name for zone. Different profilers use different names for the same thing. Here it's just called span. It basically stands for the zone. Now Rust does have destructors, so the zone will be closed in the drop implementation, so that you don't have to call end manually. And if you want to also profile window present, you can just start a scope with curly braces and add another span passing in the zone name. So now let's record it. Now before running the app, I suggest you to run these two commands. They mount the kernel tracing system. They allow Tracy to collect context switch data, which comes quite useful. So then you run the target program, you run the profiler UI, and you see this kind of panel. Here you can enter the IP address of the client to connect. So Tracy can actually profile over network, which is very useful. We'll see it coming handy later. But also here at the bottom, it has these discovered clients, where it should show your running program on your local PC. So I will just click on it, and it will open a view like this, which will be scrolling to the right because it's recording data. And here at the panel at the top left, it will say query backlog, which is how much information is left to receive from the target program. So now you do whatever you want to profile, then you close the program or click stop, and you see the timeline. You can zoom and pan around it. Here I've zoomed out it fully. So this is 50 seconds of recording. This is our timeline. You can see two big sections here. At the top, the CPU scheduling. It shows what each of the CPU cores is doing at every moment. And at the bottom are our zones. The zones are split by threads. Here you can see main thread in the middle, as well as Tracy sampling, Tracy symbol worker. So for the main thread, we annotated our zone. The activate call happens only once and in the beginning, so it's just this tiny rectangle. But for other threads, where we didn't annotate anything, Tracy will actually sample call stacks and emit those ghost zones where it tries to show the zones based on call stacks. So I can zoom in to our marked zone. This is it zoomed in. You can see my activate and below it window present, because window present is inside my activate. And if I hover over it, it will show some statistics. So this took 50 milliseconds. And we can see that most of my activate is actually taken up by window present. Tracy also collects a lot of information for us without me annotating anything. For example, those blue circles on the timeline are call stack samples. If I mouse over, it will show me the call stack at this location of the code. Also, you can see that threads are annotated with green and red lines. So the green means that the thread is running, computing something on the CPU, and red means that the thread is currently waiting, for example, blocking reading from a file. And if I mouse over the red region, it will actually show me the backtrace for this blocking operation. Now here you can see some symbols are unknown because I didn't have debug info installed for this library. But here is vk enumerate physical devices. So probably at this point GTK went to open my GPU through Vulkan, and is currently waiting for the driver to give it back the handle to the GPU. So now you can see to the left of my activate there is a big empty region, and my guess is that this is GTK init and adwite init, and let's verify this. Let's go to our main and put the zones around GTK init and adwite init. Now keep in mind, in C there are no destructors, and you have to end the zone that you started, otherwise things will not record correctly. In Rust, I would just add curly braces with spans called GTK init adwite init. Now record again, and you can see all the space to the left of my activate is now taken up by GTK init and adwite init. And adwite init is taking 65 milliseconds, and you can see most of the thread is green, so it's actively computing something. How do you find out what it's actually doing? So there is a flame graph in Tracy for this. In the top panel, if you click on the flame button, it will open the split view to the bottom, which is the flame graph. It's kind of an aggregated view of all the functions. Here's our adwite init. And when I looked at this, I can see that most of this time is taken up by GTK CSS provider load internal, so most of this time is spent parsing CSS. And you can see that then it recurses down into this subdivide infos, and to actually verify that this is what's taking most of the time, there is statistics window, which presents the same information as a table, sorted by the count of like samples, call stack samples. You can see that subdivide infos is indeed at the top, so this is our hottest function. So while making the slides, I noticed something weird. This is adwite style manager constructed. For some reason, it's loading CSS twice. And we did a small investigation with Alice, and it turned out that the first time it was loading like the basic default CSS, and then it was loading properties such as dark style changed or reduced motion, high contrast. If any of those were non-default, it would change the CSS and load it twice. And thankfully, it was an easy fix by Alice, which went into 51.alpha. So now adwite style manager only loads CSS once in the end. And so it became like 1/3 faster, which is nice. GTK, I mean, Tracy has quite a bit of nice functionality for inspecting repeatedly called functions. So my activate was only called once. What if we instrument some repeatedly called function? Let's try GTK's frame clock. So this is inside GTK now. The frame clock is an object that controls the whole repainting cycle of the app. So it's called every time, like every frame. So I'm adding Tracy zones around some existing GTK instrumentation. And recording with Tracy, the icon scroll demo. If you're unfamiliar, an icon scroll is a GTK demo, which loads like a few hundred icons, and then continuously scrolls them up and down. so it's always repainting. Here's my 15-second recording with 2000 zones, which are too small to display. I zoom in, and I can see that these are my GTK frame clock paint idle zones, and there are also some zone at the bottom because I annotated something else there. And it's taking 1 millisecond. So it seems to be fine, but how do we actually tell like where in the monitor repaint cycle this happens? Like are we losing any frames or not? Thankfully, one of the pieces of data that Tracy collects for us are DRM vBlank events. So it collects when the monitor actually repaints. There's this gray line at the top, frames. I can click on this, and now it highlights. It also shows this green-red display at the top. And these are the frame boundaries. So these ticks here show when my monitor actually repaints. And so you can see that these GTK frame clock zones happen pretty early in the frame, terminate well before the next frame. So we are seeing that everything is good. We are not dropping any frames. Now, if I click on this zone, I will see this window at the top left. If I click on the statistics button, I can see a statistics panel on the right. So this will show aggregate statistics over every single call to this function, essentially. And they both have some digit like time information, so mean duration, median duration, percentiles, as well as this yellow histogram. So this yellow histogram aggregates, once again, every call to this function. So on the horizontal axis, we can see the duration, and on the vertical axis is how many calls hit that duration. So we can see that most of the calls were around 1 millisecond in length, which is pretty good. But also here, it's very hard to see, but there are like 2 calls here which are very long. How do you find? Thankfully, this table at the bottom, if I expand this main thread group, Tracy will show me every single instance of this zone, and I can sort by execution time. And here are my 300 millisecond call. Then the next one is like 6 millisecond, and then there are a bunch of 2.5 millisecond. Now I can actually middle click on any of those rows, and this will zoom the timeline view to that exact zone that I selected here. So this is our 300 millisecond zone. Now, once again, how do we find out what the code was actually doing? We use the flame graph. In this case, I click the limit range checkbox, which limits it to just the timeline. And here you can see most of it is like GTK widget do snapshot. If I scroll it a bit down, then it comes down to GTK texture new. So basically, in this call, it's just loading all of those hundreds of icons. So it's expected that it takes this long. I don't know, maybe if I were to optimize this, maybe I would load icons in multiple threads. But basically, this is not unexpected. Now let's instead explore one of those 2.5 millisecond calls. And here's one of those zones. I middle clicked, so the timeline zoomed to it. And here you can see the code is waiting for something several times. So if I mouse over one of those red areas, you can see a call stack which says something like GTK surface update size, GTK Vulkan context check swap chain. So these are the moments when I resized the window, and GTK seemingly went to Vulkan to like renegotiate the surface and the swap chain. So I'm not sure why it's blocking for like six different times here. Maybe something to optimize here as well. But it's clearly visible. Now, as part of my profiling work, I instrumented Mutter, which is the compositor. I have this merge request open if you want to take a look. And let's see what kind of considerations there are when instrumenting Mutter. So Mutter actually has existing Coggle trace instrumentation, which emits sysprof marks. But as I said before, sysprof marks and Tracy zones are basically the same thing. So I just took these existing macros and made them also emit Tracy zones with Tracy czone end, passing in the name and ending. And the Mutter macros actually use this GCC extension, attribute cleanup, which is kind of like a destructor, so you don't have to close the zones manually. One important thing about Mutter, which is GNOME's compositor, is that you're running it constantly. Like you don't just open it and then close it. It's always running. It's your session. So by default, Tracy will collect data always from program startup until you connect with the profiler. Then it will upload all of this data. So you can profile from the program startup. And here we instead want the on-demand mode compiled with this on-demand flag, which will collect profiling data only when Tracy is actually connected. So only when you're actually profiling. So if I build Mutter, and record with Tracy, we can see a bunch of zones like this clutter frame clock dispatch, and inside it a bunch more zones. Here's the statistics for clutter frame clock dispatch. Here you can see the histogram is slightly more interesting. It has several peaks. And in this case, one of the peaks is around 10 microseconds, which is very fast, which is because when clutter frame clock dispatch notices that there's no work to do, it just returns quickly. So this is our 10 microsecond peak. But if it does actually have to redraw the screen, then this is our half a millisecond long duration. You can also see here that I'm grouping these zones by DisplayPort 1 and DisplayPort 2. So I have two monitors connected, and I want to group the zones by the monitor so I can see separately if one of my monitors takes longer to redraw compared to the other. You can do this by Tracy zone text, which lets you attach an arbitrary string to a Tracy zone. And then in this UI, you can group by user text and filter and group them by this user text, which is quite useful. Tracy can also do plots with the Tracy cplot macro. Quite simple, just pass in the name and the current value. This is how they show up. These are a bunch of plots that I added to Mutter, like the GPU time that it took to complete the frame. And the nice thing about Tracy plots is that their minimum and maximum ranges always automatically adapts to what you see on screen. So let's say that I want to look at this region in more detail. I zoom into it on the timeline. And you can see that the plots readjusted themselves, their minimum and maximum, to the values that are currently visible, which makes it very easy and convenient to inspect a particular bed frame. Now, Mutter is good and all, but we also have the whole GNOME Shell on top with the JavaScript UI. So how do we profile that? I decided to instrument GGS, which is GNOME's JavaScript engine. And in particular, I decided to instrument the places which call from C to JS and from JS back to C. GGS has this one convenient function invoke, which calls from JS to C. It first converts arguments from JS to C, then prepares a native call, then actually calls the function with this FFI call. So I put a zone around it. But the problem with GGS is it's not only used in GNOME Shell, it's also used in a bunch of other apps. And you don't want your Tracy profiler to be running in all the other apps, only in GNOME Shell. So here I will check if Tracy is started and is connected, and only then will I create an actual active Tracy zone. You can see I'm passing 0 here, so this is not active. And this would work fine. But it would name all the zones like function invoke, which would not be very descriptive. We want to actually know which function we're calling. Thankfully, GGS can provide a name here of the function. And then we can use this Tracy alloc srcloc, which is the function which Tracy czone macro expands into. We can manually call it and pass it the name. And this will set the custom name for our zone. So now if I record a Mutter, well, first of all, another consideration. For these libraries, which are used in a bunch of applications, you also need delayed init and manual lifetime compile flags, which make it so Tracy is not even initialized until you call this Tracy startup profiler. So in Mutter, in meta create context, I added the Tracy startup profiler call. So in Mutter, Tracy will start up and run, but in all other programs that use GGS, it will be completely inactive, will not affect performance in any way. So now, if I record Mutter and GNOME Shell, I can see that in addition to the Mutter zones that you saw previously, there are also these colored JavaScript zones. And the colors are actually something that you can add. So you can set Tracy zone color with RGB hex color value. And the way I colored this is every function call from C to JS is colored teal, and every call from JS back to C is called purple. And this makes it easy to see that, for example, when we're handling event, we're calling JavaScript handle event, then it's calling back to C emitting an update signal, then that is calling JavaScript update touchpad gesture, which is calling back into C emitting update signal, which is calling some more JavaScript switch workspace. And every one of those calls, it adds a little bit of overhead. And thankfully, this kind of coloring makes it very easy to see when it's happening. And you can easily debug when something is going wrong here. Finally, one more thing that Tracy can do is profile memory allocations. For this, you need to wrap or instrument the allocator. Now, Rust makes it really easy because you can override the global allocator with the profiled allocator. In C, you can override operator new and delete, adding the Tracy instrumentation. Now, of course, this will only work on allocations from Rust and C allocators, respectively. For C, there is no easy option. You'd need to instrument glib with the gmalloc and gfree macros, or do something similar to sysprof memory collector, which hooks with LDP reload and instruments malloc and free. I will show an example from niri. So I got a bug report that locking and unlocking the screen would increase the memory usage. And in this test, I'm locking and unlocking the screen 4 times. And you can see on this memory usage graph, indeed, after every unlock, the memory usage is increasing. It's not going back. So in the memory table, Tracy will actually show me all active allocations, so allocations that have not been freed by the end of the profile, and it will allow me to inspect the call stacks. When I was inspecting the call stacks, hovering over the source code shows me the source line. I noticed that a lot of these allocations were for Wayland objects, so my theory was that there was some kind of reference cycle where a Wayland object was referring back to itself. I went looking in the code. Indeed, the log surface object contained this surface, which is basically a strong pointer back to itself, and it was never freed due to this reference cycle. So the fix was to make it a weak reference instead. And after this, you can see I recorded again. After each unlock, the memory returns back to where it was, so the memory leak was fixed. Also, this memory view has this nice tree. Where Tracy shows you how many kilobytes you allocated from every part of your code, which also makes it easy to see when some part of your code is doing a lot of unnecessary allocations. Now let's actually try to do a demo. So I have this OnePlus phone here, which runs post-market OS and mobile shell. And it runs with my patches, so I will try to connect to it. The GUADEC Wi-Fi doesn't provide automatic discovery, but I happen to know the IP address. So I can connect. So you can see Tracy started recording. Now I can do something in the shell, so we have a little bit of data. Now once I'm satisfied, I will click stop. Let me maximize, dismiss this. And so this is our timeline. I can zoom it, I can pan it around. Hide the CPU data. So sometimes these ghost zones kind of take up all of the space. But you can just, you can disable them in settings, or you can scroll down. Here's our main thread. Here is our zones. You can see my coloring. We can click at frame clock dispatch. We can view the statistics. Here you can see the times. This is where you can inspect the the longest function, and yeah, the call stacks as well. So this is where the network profiling is most useful when you have some other device, like a phone, and you don't need to run the full profiler UI on the phone. You can run it on your laptop, where you can inspect it on a big screen. Makes it quite convenient. So if Tracy is so good, why not Tracy? Why aren't we adding it to all of our libraries? Well, the main point is probably that it's a bit awkward to package. So as you saw, some important toggles in libtracy are build time. This is made this way because for game development, you really want to minimize the overhead. So it literally compiles out all of the unneeded code. But unfortunately for distribution, system-wide profiling, it means that I have to make separate packages with different build flags. For example, network profiling is cool, but by default, you really don't want someone else to be able to connect to your computer. So the default build here disables it, and you need to install the Tracy broadcast package to enable it back. And for another example, this no call stack. So I found that the call stack Ansible resolution is quite heavy, sometimes contends with GGS. So for Mutter profiling, I would recommend maybe Tracy no call stack. But this has to be separate compilation, separately compiled packages, not very convenient. Also, at the moment, in Tracy, there's only minimal support for multi-process and whole system profiling, which is where sysprof kind of really shines. Would be nice to see more support there. So, as I said, Tracy and sysprof basically collect the same data. Tracy zones and sysprof marks are basically the same thing, save for one requirement. So, all of these useful views could, in theory, be implemented in sysprof. And I would say that the most useful is this timeline view with nested marks and with all of this information available in one place, where it's very easy to zoom into specific frames and see why specific frames were very long. and like see if your frame went to do a blocking read somewhere. So Tracy makes this very easy by showing the information in this unified graph where you can zoom in and dive into like some specific call. Also, mark statistics, histograms, better sorting and filtering I found very useful in Tracy, how you can click on a function and see like the time distribution. We could do this in sysprof as well. We don't have to rely on Tracy necessarily. So as a recap, for C, build with libtracy, markup with Tracy czone and other functions, see the Tracy manual. For us to use Tracy client, make sure you have frame pointers and debug info for good stack traces. Thankfully, modern distributions are building with frame pointers by default. It is very helpful. If you have broken stack traces, most likely you don't have frame pointers. Run these two commands before profiling. And remember the flags on demand for long-running processes, such as compositors, and delay the need plus manual lifetime if you want to instrument libraries such as GDK or GGS in this case. So that's all I've got. Thank you. If you have any questions, I would be delighted to answer them.
If people at home have questions, now is the time.
Hey, really cool. I wish we would all do more of the profiling stuff, so I'm very happy that someone's looking at this. But one question I have is essentially, what would it require to remove like the friction in the process here? Like having to recompile everything and adding the I don't know, instrumentation is a bit awkward, I guess, and makes it, you have to know all the weird parameters and all the interesting libraries that are packaged and whatever. So is there a way we can get streamline all of this?
So I have two answers here. The first one is this is like not really Tracy specific. We already have a bunch of sysprof instrumentations in a bunch of our projects like Mutter and GGS. So this is kind of a similar deal here. Once again, maybe if we add more displays to sysprof, then we can just use sysprof where everything is already instrumented. And the second thing is, so all of this data that Tracy automatically collects, like call stacks and frame data, I think they recently added a binary utility which can connect to a running process and like without having to instrument it. I haven't tried it yet. Really what you're instrumenting by hand are like manually marked up zones for the interesting places that you want to see in your code. And also you can mark up like GPU zones. Otherwise, like many parts of Tracy can work even without manual instrumentation. But yeah, it's an understandable pain point.
Thank you. Any other questions?
Thank you. This is really cool, by the way. If I wanted to look at the interaction between GNOME Calendar and Evolution Data Server, does it help me look at different processes together?
So this is what I mentioned by like minimal support for multiprocess. Actually, on Git, I found that there are some first steps towards multiprocess recording with Tracy, where you can run 2 or multiple capture sessions at the same time, and then there is a binary to like merge the data together and view them as one single like Tracy view. So I guess instead of threads, it will show you processes. But from what I've read, it's still rather limited. So it will drop a bunch of data from that recording. So hopefully in the future, people will work on like more multi-process profiling. That would be great because yeah, right now this is one of the things that Tracy is not very good at compared to sysprof.
All right, thank you.
Any other questions, comments? Well, Well, I think that's it. Thank you so much.